So here we are with another one of these questions with the stub impedance matching, but this one is a little more unconventional than most questions in that we might have to work backwards to actually solve the problem, as opposed to the traditional train of thought where we have when we're given load conditions and we find stub placement. Here we're given the stub placement, but we need to find load conditions. So we are given a stub of length 0.12 lambda is used to match a 60 ohm lossless line to a load. If the stub is located at 0.3 lambda from the load, determine the load impedance ZL, the length of an alternative stub and its location with respect to the load, and the standing wave ratio between the stub and the load. So, there are a few pieces of information given in the question that are very important, that are absolutely critical, not very important, they are critical to solving this problem. So you have a stub of length 0.12, and then you have the stub is located at 0.3 from the load. So these two pieces of information here are going to help us solve the problem. Without these two pieces of information, we can do absolutely nothing. So we'll start with part A. If you recall, we said that the length of the stub we define as d, so that's going to be 0.12 lambda, and then we have the distance from the load, which we define as L, which is actually going to be 0.3 lambda. But what did we actually define these things as in terms of the Smith chart? If you recall, d is actually the distance from PSC. So this is the distance from PSC to a point on Smith chart edge where S circle and R equals 1 or G equals 1, depending on if you're using admittance or impedance, circles intersect. Now, what do I mean by edge, or the Smith chart edge? Because that might not be very clear. We'll get to that in a sec. But first, I want to also define this, just so we can understand how these things are actually going to help us. So this is the distance from the intersection of R equals 1, again, or G equals 1, circles, circle, and S circle. So it's that distance from that intersection between those two circles to the load. Okay, so the second one's relatively simple because it's from the load you go to the intersection, but the first one, the way it's probably worded might be a little more confusing than anything else. In any case, if you recall, I say I always like to draw the R equals 1 circle. Whether or not you need to draw it in your solution is entirely up to you, but for me, I feel like I can visualize the problem a little better if I can see this circle. In general, let's say we usually have some circle here. That means I'll have 2 points of intersection here. Now, if you remember, what we did when we solved these problems, we would take this and we would, project it onto here and then draw the dot here. And then I would draw a line from here to here. And then this distance I called D. And I did this in where I laid the foundation of the stub impedance matching techniques. I called this distance D. If you haven't seen that video, I will leave a link in the description below. I would highly recommend you look at that. All of these problems will make a lot more sense after that. So this distance D then that we're given here is essentially this distance here that I've drawn. Well, not this distance, but it'll be this distance measured across this. Here I've gone a much larger than 0.12, but in our case we want to go 0.12. So let's get rid of this, all this sort of explanation rough work, and what we'll do is we'll actually draw our the distance that we actually have. So I'm going to start from here, and we know PSC is here. And if you don't know that by now, then I guess we need to review, definitely. So you go from here, and this is 0.25, and I want to go 0.12 lambda. So 0.12 lambda is actually going to be this point right here. So 0.37 or 0.13 if you're looking at the inner scale. I'll use the outer scale here. I like to use the outer scale, generally speaking. unless some specific reason not to. So this here is actually my D, and so from here to here I call D. So the actual point here is along the edge, so to speak. But what is this point in terms of the actual S circle? It's actually this intersection here. Okay. If you remember from that video, we defined this bottom point as A prime, and I defined this intersection here as B. Now we know from symmetry that this bottom point A prime is going to have a corresponding point the exact same at the top, B prime. But first, what I will do is I'll just give this a value. That looks like it's about y equals minus j 1.06. And so therefore I must have, well, this is normalized, and therefore I must have a corresponding value at the top, which will be the opposite due to the symmetry of the circle. So if this is minus 1.06, then the one at the top must be plus 1.06. And what I will do then is, I don't really need to even draw a line through that. We might need to later on, but for now let's just not, because it's going to make it very messy very fast. We call that point B prime, and we call the point where it intersects with this circle here A. Now the next step, once we found these points, is to actually find the circle. Now when we find these points in the other case where we're going forward, and by forward I mean we start with the load, we draw the circle and do that. We draw the circle such that it goes through these points, because these 2 points must fall in the S circle, and we know this to be true from all of the relevant theory. So I have here my S circle, and I will try to place it such that both points get included, and I think that, well, maybe I could do a little better than that. There. I think that's good enough, close enough for the intents of explanation at least. Your circle will be perfect, but mine will be a little off just because I'm doing it here. It's a little difficult. So, you'll notice I left these subscripts blank here. There's no subscript here, no subscript here. But we must have a subscript since there are two actual stubs we can have. One of them must correspond to A and one of them must correspond to B. The definition of D, of this here, from this distance to A prime, we actually call this variable here dA. And so that corresponds to this stub here. So the distance from PSC to dA actually corresponds to the stub on the top. And that is just a convention, which actually comes from the fact that it's admittances and that we're actually going in the opposite direction on that. I mean, you can get into all the nitty-gritty details, but I guess the thing to take away is point A prime corresponds to A, point B prime corresponds to B. So this distance then here is dA, and this is LA correspondingly. So now we have dA and LA, so it's looking pretty close to the kind of circles or the kind of concepts or the questions that we're used to dealing with. So now the next piece of information we need to use is LA. So the LA is actually the distance from the intersection of R equals 1 or G equals 1 circle and the S circle to the load. So we said that we're using point A because we said dA is the distance we're given. So then we're assuming that our stub is placed at load A. This distance here is actually, or well, that point I should say, not distance. This is actually 0.164 lambda, and I'm using the outer scale there. So that's this point. So now I need to travel from this point to my load, and I need to go 0.3 lambda towards my load to get there. So towards my load is counterclockwise, but the thing to realize, well, I guess we'll get there in a few seconds. I shouldn't jump ahead yet. But the way I usually like to go around the Smith chart when it comes to larger than quarter lambda movement, and I say quarter lambda because that's usually half, and so anything beyond half you can kind of simplify a little bit, either by geometry or some sort of symmetry. But what I really mean is that from here, this point, This point to this point is 0.164 lambda. Now how do I know that? If I'm looking at the middle scale, or if I look at the outer scale, whichever one really. The outer scale kind of shows it better in this case, because at this point on the outer scale I'm 0, and at this point I'm 0.16. The inner scale at the same time says 0, but you should realize that these numbers are actually increasing, so that actually represents 0.5 and not 0. So you'll have to add a factor of lambda over 2 if you really want to get that. So in this case, it's easier to use the outer scale, so I'll use the outer scale. So I know that if I've traveled that far, I've gotten 0.164. So now if I want to go from the 0.164 here, I need to go a remainder, but I still need to go 0.3, right? So 0.3 is what they asked for, and I've already gone 0.164. This difference is actually 0.136. So now I need to go an additional 0.136. Now here you'll notice it's easier to use the middle scale because the middle scale starts at 0 here and it goes up to 0.13 or 0.136 is what we want. So let's draw a line at 0.136. 0.13 is here. This is 0.132, 0.134, and we'll call this 0.136. Now, the intersection on the circle is our point of interest. Okay, and so I will draw a little line off and I'll call this YL. YL is the thing to note here. If you go back to our definitions or go back to our procedure on how to solve these problems, whenever we're dealing with the load, we deal with YL. Now the reason for that is because we're dealing with the parallel shorted stub. And when we're dealing with circuits in parallel, it's usually easier to deal with admittances, simply because in admittances, if they're in parallel, you can actually add them straight up, whereas impedances, you usually have the inverse relationship, the 1 over z plus, or 1 over z is going to be equal to 1 over z1 plus 1 over z2, and so on and so forth. And so in this case, we deal with YL. So that distance is actually to YL and not ZL. But you'll notice the question asks us for ZL. So now how can we find ZL given this information? If you've seen any of the other videos, or if you just, I guess we can reason that the inverse of this thing must be on the opposite side in terms of magnitude as well as phased. So on the opposite side, I've drawn a line through my point of interest here, which is the load, as well as the origin, and then I find this intersection on the other side of the circle. So this point here is ZL normalized. Now it might not be very clear on the Smith chart, so what I will do here is I'll write that ZL normalized is actually 0.57 plus J 0.69. So what's the actual value of ZL? The actual value of ZL is just going to be 60, which is a characteristic impedance, times this normalized value. And if I multiply that out, I will find that I have ZL is going to be 0.342 plus J 4 point, sorry, not 4 points, 41.4 ohms. And so that now is my ZL. So we've completed the first part. Okay. Now it says part B asks, it says a length of you want to find the length of an alternative stub and its location with respect to the load. So if you're familiar with this sort of procedure, you might remember that dB plus dA equals lambda over 2. And this is always true. So if I have dA, I can find dB. So this is going to be 0.5 minus 0.12 lambda. And so dB is going to be 0.38 lambda. So I know dB. But at the same time, I could have found dB just by looking at the Smith chart. In any case, I mean, when you look at the Smith chart, you get 0.37. If you do the calculation, you get 0.38. They're relatively close. This approach here is more of an approximation. So this calculation is really an approximation, I guess you could say. So simple rounding errors might cause the numbers here to be here and there to be different. But still, you should get a number that's more or less the same. In any case, we'll use, I guess we can use the graphical solution, since the graphical solution will probably make it easier for us to solve. So what I'll say is, I'll call it then 0.37. And I'll make a note here from Smith chart. Because the thing really is, I mean, we go from PSC and we go around this way towards the generator, and essentially we want to get to this point here. And if you look at that, I mean, if I run a line between the origin and B prime, it falls exactly on 0.37 right there. And so, I mean, it's not very difficult to see that, you know, that is 0.37. So I guess we can keep that line there because we'll need that to go towards the load. So let's keep that line there. I think at this point we can get rid of this line here just because it's really just getting in the way. Now, we want to find the distance between B prime and the load. So I want to travel from B prime to the load. Now, here's the part that might be a little confusing or might cause a little trouble. I am at B prime. Sorry, I should be at B, not B prime. B prime is that actual distance. I've been talking about B prime. I should be talking about B. B is where the stub is, not B prime. B prime is where the projection of the stub thing goes to. So I guess I really don't need this line then. So let's redraw that line down here, and we have a lot of lines down here, so we should be very careful. So maybe I can just, try to make this look a little better. So this is YL. I'll probably get rid of this, just because it's messy now. So, okay. So I'm at point B here. This is where my stub is. The same way stub A was at this point, stub B is at this point. Now, how far is this point from YL? And you'll note I have to go to YL, not ZL, because whenever we're dealing with parallel stubs, we go with admittances. So, and again, it's not, I can't just say it's this small distance here. I have to take this whole distance around because I have to go towards the load, not towards the generator. So I need to go all the way around this way. Rather than go all the way around that way, I think the simpler way might be to just find what this separation is and then subtract that separation from half lambda. Because I know one whole revolution is half lambda, and then this separation will just be, that half lambda subtracted this separation will give me what this, well, I can't really see that clearly. Half lambda minus that little separation will give me this whole distance. So if I just zoom in for a sec here, and I'm literally just going to count it off. So this is point here, this is point 2 here, point 4, point 6. So this distance is 0.006 lambda. And this from here to here is 0.02. So this is 0.02 lambda. And then now this is going to be 0.002. This separation is 0.002 lambda. So if I add all these together, what I get is I will get 0.02 plus, so I get 0.02 plus 0.008 essentially. So I get 0.028 lambda. So now I take 0.5 lambda and I subtract 0.028 from that, and I get 47 or 0.472 lambda. And so 0.472 lambda is the distance from this point to this point. Now, rather than go all the way around and calculate it that way, I find it easier to just take that little difference. I mean, if you have small differences, it's usually easier to calculate this way. So I guess it's just a matter of doing more problems and figuring out which is the simplest way to get from point A, or from one point to the other. So, and this right here is actually LB. So I can probably go ahead and write that here. And so let's write LB is 0.472 lambda. And dB, we already know, we said 0.37 or 0.38, whichever one you really want to take, I guess. You know, they're close enough that you can really choose whichever one you want. Now, SWR. How do I find the SWR between the load and the stub? The SWR between the load and the stub is simply that, the length of that line right there. So, in other words, it's just this intersection here. And if you were to actually look at that intersection and you were to actually have a thin enough line where you could see it clearly, you would find that the SWR is 2.65. And so that is your SWR. So we've done the length of the alternate stub, and we've solved the standing wave ratio between the stub and the load. So things to note here. You should be able to work forwards and backwards. Given the length of the stub and the location of the stub, we should be able to find load conditions. Given the load conditions, we should be able to find stub and stub length and location, as we have seen in previous questions. Other than that, what we need to look at is we make sure that we're always dealing with the load in terms of YL and not ZL. ZL we would use as an initial placement maybe if we didn't want to convert, but after that we deal with YL. Whenever we're moving towards the load, away from the load, we're always talking about YL and not ZL. So I hope you found this video helpful. If you haven't already, hit that subscribe button so that we can actually get videos to you, or you can actually get notifications as soon as we have videos posted. And if you have any questions, feel free to leave them down below and we'll get back to you as soon as possible. And other than that, I want to thank you guys for watching. I hope you found everything helpful, and we'll see you in the next one.